Okay, good afternoon, everyone. How did the homework go? Do you have any questions about the homework, the practice problems, or anything? Anybody? Okay, so we gonna finish the worksheet I started last time, and then we move forward. Okay, so if you have no questions, and we will do that. Now I did put it on bright space, so you guys will follow me while we're doing it. I don't have to write it. So last time we went through problem number 1, and then we started number 2. So let us do it. And as I'm doing it, I definitely would like your input for every questions. So here is our problem. Okay. So we have a binary string. It's a string that consists of 0s and 1. We did that. So the question here was, how many binary string of length 7 can we make? And since it's just zeros or 1, 2, 3, 4, 5, 6, 7, and we had 2 choices for each, and then we have the 2 to the power 7. Okay. And then part B, no, I forgot that we did all of that. Okay, how many string of length 7 can be made that have exactly 4 ones? So we have those 1, 2, 3, 4, 5, 6, 7. Exactly for 1. And the logic we said, okay, then first we have to position the 1. Crucial. We first position the 1. And the idea is, in how many ways can we position 1? And we said that every time we position them correspond to a subset of 1 through 7. Because every position, so the subset 1, 2, 3 correspond to position of 1, 2, 4 correspond to position here, 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 and here. The positions that you see correspond to 2, 4, 6, 7. So the number of ways we can pick those positions is the number of ways we can pick 4 out of 7. That's the number of positions. Now the rest, because we have just binary, will have to be a bunch of zeros. So the answer is going to be 7, 4. Okay, so that's what we did last time. Now I would like you to want to take the second one and proceed. Okay. Right. Do you guys have the sheet with you? Yes or no?
Yeah, it just took me a second to find it, but I found it.
Yeah. Everybody else? Great. So I can write on it. I don't have.
I tried to find it. I don't know where section.
Go to content. Go to where I put the practice problems. With me?
Yeah.
Yeah, on the top, there is the practice problem that I wanted you guys to do for today. And I also, or Nick is giving you another hint. Look for the date, 9/23, and should find it. Did you find it? Okay, I hope you did. So now you guys will have to help me. We would like to form strings of length 10, but they contain 3 digits, the 0, the 1, and the 2. So they're not binary anymore. And my first question is, how many strings can we form? Okay, so 1, 2, 3, 10 of them. All right, so flip, yeah, 10, okay. Quickly, how many can we form? Now I expect your answers. Any answer? Anybody? 3 to the power 10 is still correct. Absolutely. We have 3 choices here. For every choice, we have 3, we have 3, we have 3. So 3 to the power 10. Okay. Now, how many strings contain exactly 4 ones? So I'm still emphasizing, you know, how we do that. So exactly 4 ones. So we have 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many exactly 4 ones? So that's the picture. I want exactly 4, not more. 2, 3, 4. That's what I want. And then the rest could be anything. All right. How would we answer this question?
Would it be the permutation of 10 and 4?
No, that's not a permutation. This one? That's what you mean?
Yes.
That's not a permutation. That's a combination.
Oh, sorry, I got confused.
Yeah, that's okay. Permutation, it's nothing more than you have 4 different numbers and you are putting them in different order. So they are distinct, sorry, permutation, let me make sure. If I put P10 4, what's the picture in my mind? Picture is the following. I have 10 different objects. Okay, that's a picture in my mind. And in how many ways I can make a list of linked 4 using those 10 different objects. That's a permutation. So if my objects are A, B, C, whatever. Actually, that's it. Let me use 1, 2, 3. 1, 2, 3, all the way to 10. So permutation, it means this is the scenario I'm looking at. 3, 2, 1, 4, and so on and so forth. Combination, or 10 choose 4, it means I'm just picking 4 out of those 10. I don't care about the order in which they shows up. Is that clear?
Yes, thank you.
Sure, it's crucial, it's crucial. So here, when I am positioning those 1, do I care about the order in which I am putting them, or I care only about the position? The order doesn't matter because it's the same number. So 1, 1, 1, 1. So what I'm really thinking about here is in how many ways I can pick 4 position out of 10 position. That's really what is 10 choose 4 here. It means I want to pick 4 position out of a 10. So how many I can position? So the number of ways to position the 4 1, to position the ones is 10 choose 4. So the number of ways I can pick 4 out of 10. So if I pick, for example, 1, 3, 4, 5, it means I'm positioning my ones in spot 1, spot 3, spot 4, spot 5. Okay, all right. Am I done? Am I done? How are we gonna keep thinking about it? For each fixed position, once I position my 1, how many ways are there to put the rest? But I still have 2 digits, 1, 2, 0, and 2. In how many ways I can do that? So I positioned my 1, I fixed it here. But then I have all those left. In how many ways I can, how many choices I have for those? 2 to the power 6, do you agree with Nick? Absolutely, because I have 2 to the power 6. So now what's gonna be the answer? That's now what way we use the product rule. So there are that many ways to position them. For each fixed position, I have 2 to the power 6 ways to position the others. And that's gonna be my total number. Please ask questions if you have any issues. It's crucial. Now, how many strings contain exactly 4 ones and exactly 3 2s. Okay, I'll give you a little bit to think about that, unless you've done it.
Can you clarify something for me on part B?
Absolutely. Go on.
So when you're doing 10 choose 4, that's how you get the amount of exactly 1. And when we're multiplying by 2 to the 6, is that just if we want to determine how many different orders can be made in the string?
Let me repeat how I'm thinking about it one more time. And let's see, probably that's what you're saying. Once I position those ones, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. I put them here, put them here, put them here, put them here. I fix this position. That's what they stand for. There are that many ways to fix them. Now, if I fix those, how many possibilities I can play with? I can put 0 here, right? 0 everywhere. Or those are fixed. Those are the one I don't change. But then I can put 2 here, 0 here, 0 here, 0 here, 0 here. Or those are fixed. But this I can put, I don't know, 2 here. I can put 2 here, 0, 0, 0. So the question is, when I fix those, that's really the way we're thinking. When I fix those, in how many ways I can change the rest? In how many ways I can change the rest? So those are fixed. I don't really worry about them. In how many ways? This one, I have 2 ways to change it. I can put a 0 or a 2. For each one of those, I have 2 choices for that. For each one of those, I have 2 choices. For each one, I have 2 choices. I have 2 choices. So if I have 10, 4 are taken care of. I have 2 to the power 6 choices. That's where the 2 to the 6 for, because I have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. I needed 1 more. Okay, so you fix those in your mind. Those are not changing anymore. You want to fill the rest. In how many ways? Okay, for each one, you have 2. For each one of those, so this one has 2, 0 or 2. For every one, this one have 2 choices. So I have already 4 for the first 2, 8, and so on and so forth. Okay? Is it making any better sense or not yet?
Yes.
That's the picture. Your 4, those are fixed. You're not changing them. You worry about the left. And there are 2 to the power 6 ways to do them. So that's why when I'm writing here, for each fixed position of the ones, there are that many to put the 0 and the 2. So once you fix those, that's how many you have to play with the rest. But then why I multiply by 10, 10 choose 4? Because there are that many ways to pick the ones. So for this one, 2 to the 6. If I change the position of the ones, then I'm going to change. So if I change the positions, I change the position. I have a whole different scenario. I have another 2 to the 6 because this would be 3 and those are my fixed position. So now I have again 0, 2, 0, 2, and so on and so forth. Right? Okay. Now I want you guys to do number C. Yeah, I want you to think about it. Try to think about the way I'm trying to and see what we can do.
So the first part is kind of like B, right? It would be 10 choose 4 to have
That's the
exactly
first
4
part.
ones.
Yeah, so I'm gonna draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And I need more. Very good. All right. Repeat what you said because I think what you said is correct.
The first part would be 10 choose 4.
Right. First, we position the ones. So number of ways to position the ones. The ones is, we have 4 position, we have to choose 4 position out of 10. So now in my head, I positioned my 1. Very good. Keep going.
And then for the 2s, would it be 6, choose 3? Because we only have 6
Exactly. Now
places
I
left.
have 3 spots, sorry, 6 spots left. Okay, now I'm going to think. So for every fixed position of the 1, so once I fix the position, once I fix that, so for each fixed position, as you realize, I'm keep writing fixed because that's where I want you to think about that. For every fixed position of 1s, there are, okay, so we still have 6 spots left, and I need to pick 3 out of them. Okay, so now I have, I'm putting what? I'm putting 2s. So now I have my 2s. And there are how many ways? There are 6 to 3 ways. Now, because I only have 3 digits, so now the scenario is done. The leftover will be having only 0. So I don't really have to do anything. So what's going to be the answer now? The number of ways we can fix the ones. For each one of them, there are that many ways to fix the 6. And now we can compute this. So let us just compute it because we have to also figure this out and being able to, at the same time, remember the formula. So the first one will give me, it's a 6 factorial over 3 factorial, 6 minus 3. So you have to memorize the formula verbatim times 10 factorial over 4 factorial and 6 factorial. We're lucky. Das and das will simplify. And I will be left with 10 factorial divided by that. Okay, and then we compute. I don't feel like computing. Okay. All right. Party. How many strings contain at least 3 ones? Okay, ideas. Okay.
So when it's at
I'm
least
listening.
ones, wouldn't it be it'd be 10 choose 3, and the rest would be 7 choose 3?
So 10 choose 3, it means you're picking the 3, right?
Yeah, at least.
Okay. Yeah, this will pick 3. This will pick exactly 3. That's what 10 choose 3 is. The number of ways we can pick 3.
Yes.
And then what you're going to do is the left.
7 choose 3?
7 choose 3. So now I lost you. What does the 7 choose 3 represent?
Because if we at least choose like 3 ones, they want it at least.
Okay, so I chose those 3 positions. And then?
my thought was you can still like choose more. You can still add more ones to it. So
So you're picking something like that?
yes, I might be wrong, but
Yeah, and then what do you want with the rest? What do you want with the rest? And if you choose those, it means you're basically choosing 1, 2, 3, 4, 5, 6 ones. That's what we don't want.
Mhm.
Okay, so who?
Would the rest be 2 to the 7?
What do you want me to write to 2 to the 7?
To the 10 choose 3,
Okay,
because the rest of them. Oh, I guess the ones would count. So
right. If you put 2 to the 7, you're giving me exactly 3,
right.
right? I want at least 3.
Well, I know before in the notes, we did the at least one statistics faculty. We added like, with 3 ones and then with 4 ones and 5 and so on. But I'm not
Okay.
sure.
All right, we're gonna do it 2 ways: the long way and the shorter way.
So
Okay.
the short way is when we use the complement, like the passive,
Right. The short way is using the complement.
Okay.
And the longer way in this particular problem is to use what you're thinking. Okay. But why do we have to do that? Why we are forced to do that? We're forced because of the following. Remember, when we do our work, we have to make sure that we do not repeat a lot. So I'm gonna put a wrong scenario in front of you. And I want you to tell me what's wrong with my scenario, and then we're gonna fix it. All right, my scenario is like this. I have those 9, those 10, the 12. Okay, I'm gonna choose those position. So there are 3 of them. And then I say, they want at least 1, so I guaranteed the ones. And then for the rest, because 1 is allowed, so I have 3 position times 7. I'm gonna put this scenario in front of you. I want you to tell me, is it right? Is it wrong? What do you think? So I position my 1. So once I position, I have the rest. Because 1 is allowed, I can put 3, 3, 3, 3. What's wrong with this logic? What's wrong? Anybody can tell me what is it wrong in my logic? And I put it wrong. I want you to know that.
We're still talking about
The same problem.
question D, right?
Absolutely, absolutely, absolutely.
Well, that would give us exactly 3.
Yeah, that will give me, no. Why
No,
not?
2 to the 7 gives exactly 3.
Yes, 2 to the 7.
Yeah.
Yeah, yes. I want you to tell me what's wrong if I put 3 to the 7. So this gives me exactly 3. This I have no problem with it, exactly. But since I want at least, so I say, okay, I guarantee my ones, and then The rest, I have 3 choices. So, okay, 3 to the 7.
Oh, you could have ones in there then. So there could be more than. Because if we had 3, that would be the 0, 1, and 2. So you could have extra ones there. So you wouldn't be able to get an exact answer.
Because am I repeating myself?
There's an intersection, right?
Absolutely.
Yeah.
Absolutely. There is a
And
lot of
you have to-
repetition. Go ahead.
I was just saying that has to be accounted for in that case.
Right. When I do that, because I said, okay, I guaranteed my 1, and then each one will have 1, 2, 3, sorry, yeah, 0, 1, 2, because I can have more than 1. Then I have 3 choices here, 3 choices here, 3 choices here, 3 choices here. But what's really, really wrong in my argument? What's wrong is I'm going to have tons of repetition. Where the repetition is coming from. Suppose I fixed my 3 here. Remember the picture I was drawing before? And then I said, since I have 1 here, I can have 1, 0, 2, 3, whatever, no, sorry, 2, 0, 1, 2. That's scenario. But then I can tell you, suppose I fixed my 1 here. I put a 1 here. That's another position. But since I'm allowing 1 somewhere else, I can put a 1 here, and then I can replicate. Okay, so because I allow 1 on the empty spots, then there will be tremendous amount of replicate in this answer. And this is absolutely to scratch. So we have to be very careful. So the question is, what can we do to not replicate? What can we do so we don't stop repetition? And this is how we can do the problem in 2 ways. So one way is the long way. I said, I can control the problem as long as I have exactly 3 ones. I can control it. Exactly, the word exactly. If I have exactly 4 ones, I can control the problem because there will be no repetition because I only have 4. So those spots cannot have 1, so I don't have repetition. So one way we can do the problem is the following. So the first approach, we're breaking it up into scenarios that we can totally control. Okay. We can compute the number of string. I want at least that have exactly 3 plus all those exactly 4 plus etc. Those string with exactly, since I have 10 of them, exactly 10 ones. So I read it. Exactly 3 ones, exactly 4 ones, exactly 10 ones. I have to add all of them. Why exactly save the day? Because exactly I can control. That's why I can. Now, exactly 3 ones, it means I position my ones perfectly. I don't have ones to worry about because I only have exactly, so I still have 2 to be concerned with, 2 to the 7. Plus, so it's a bit tedious. Now, 4 ones. I have my ones, they are located. There is no more ones left to the 6 because I have this position. And then 2 to the 5, I pick my 5, 2 to the 4, then 4, 2 to the 3, then 3, 2 to the square, then 2, and then 2, then 1, and finally the last one, which should be 1, or 10, 0, which is exactly 1. These are the string that have exactly 10 ones. There is only 1 that satisfies this condition. Okay? So we have to add all those. Does it make sense?
Why did we start going down from, like, we went 2 to the 5 and then 10 choose 5 and then 2 to the
Okay.
4
You're
and
fixing
10
your
choose
String
4.
position.
exactly
Shouldn't
for, let's think about that. Exactly 4 ones. How many
Right.
are there? We have to pick 4 position out of 10.
Yeah,
How many are left? How many places are left?
6.
That's the 2 to the 6 come from.
Yeah, I get that, but then after that, the 2 to the 5, and then why did we go 2 to the 4?
Okay,
Or not 2 to the 4. The where it says 10 choose 4. Why is that 4? Should that be 6?
oh,
Oh yeah, that should be 6.
oh, thank you very much. My mind somehow.
And then it should be 7,
Honestly, it's
8,
the same
9.
answer, but let's fix it. So, my apology. I don't know what I thought backward. Thank you very much. That's your question?
Yeah, that was it. I was just
I'm sorry. Thank you very much.
I was confused.
You're absolutely right. That's my mistake, not yours. Okay? Very good. Now, the second approach. The second approach is to think complement. Sometimes thinking complement also is helpful. What do I mean think complement? So here I'm interested in all the string that have at least how many? At least 3 ones. Okay? So, and my universe basically is all possible strings. All possible string. All right, I want to think complement. If a string does not have at least 3 ones, how can a string fail to have at least 3 ones? I mean, what's the complement of that? How can a string fail to have at least 3 ones? Means it should have, I don't know, I don't want to answer. I'm gonna
Yeah, I have
write.
2 different ways I wrote it. I have less than 3 ones, but that I'm still like, I don't know, that's not helpful to me. But then I also wrote exactly 2 ones, but I feel like that discounts some cases.
No, you
So
cannot say exactly 2 ones. That's not right.
yeah, that's not right. I
It should be
crossed it out, but
strictly, it should be
I've
less or
less.
equal. It should be less or
Oh,
equal.
okay, yeah. Okay, I've less
Absolutely.
than. I didn't account for equal. Okay,
You have to.
okay. Yeah, I crossed off the exactly. So okay.
Right. It has to be everything. So the string that have at least 3 ones is your universe, and you have to take away from them all the string that has 2 or less ones. I take all those away.
Oh, okay. I wrote less than 3 ones, so that's the same as 2 or less than 1.
Right, because we
okay.
cannot include 3.
Yeah, it's just semantic.
It doesn't really matter. No, this is just matter of, So the string that has at least, and the math will be easier here. 3 ones is everything, but you have to take away those that have 2 or less. Now let us go back to counting those. Okay, counting those. Subtraction principle, is useful quite a bit of times. So now what's the cardinality of this set? Basic, what's the cardinality of that? It's the cardinality of the universe minus the cardinality of those.
And that should be it, right? Because there's no intersection. Or that's if you add it to the other
We
side.
have
Sorry.
nothing, there is no intersection one. That's
right, so it stops
everything
there.
minus that. Now, is it easy to compute this piece? How can I compute the cardinality of all the string? So let me take all the string that has 2 or less ones. How would you compute the cardinality of that? 2 or less. Back to you. Remember, we always break things apart to make things easy for us. So how would you break this? You want all the things that have 2 or less. So how would you do that?
Well, I think it'd just be composite of the case with exactly 2 ones, the case with exactly 1 1, and then the case with no ones,
Exactly.
right?
There is no way out. No way out. Unless you put exactly, the counting is not possible. Okay, so we're going to break it up into. And is the intersection, do they overlap those cases? String, exactly 2 ones.
No, because exactly.
Exactly, that's the word. There is no overlap because I am forcing them to have only 2 ones. Plus, those that have exactly 1 1. Oh. Plus, those that have, so the cardinality of all the string was exactly no ones. Exactly doesn't make sense here with no ones. Okay, so this is not the only 3 items. In the previous scenario, I have to take, how many? I have to take lots of problems. So let us do each one of them. Exactly 2 ones. Now we're familiar with that scenario. Means I have to pick 2 positions after 10. And then the others, I will have 2 to the power 8. Now I try not to do a mistake this time. Now exactly 1, it means there are 10 positions to put the 1, and that's 2 to the power 9. Plus, no ones, there is no one. So I basically have 2 numbers to deal with, that's 2 to the power 10. And now we go back to our set. So now the cardinality of the string with at least 3 ones is the cardinality of my universe. Now my universe is all possible scenario. My universe is 3 to the power 10. That's the universe, all possible string. And I'm going to take away, so this is, let me remind you, that's the universe, which is all possible string. That's the word I'm working with. I have to take away from it those 2. Plus 2 to the power 10. Okay, which is, I definitely think in this particular scenario, better than this whole sum. But the main idea is all those problem combinatorics. The idea is how to break the problem into situation where we can control. And in this thing, to be able to control it, I need exactly, because only when I put exactly, I can work with the problem. If I don't have exactly, then I will have so many repetition that I cannot work with the problem. Okay, please, any questions before, even though what I'm going to do now is going to be very much related to that, but any question before I move on?
So for the part where you had string that has 2 or less ones, you just broke it down with string exactly 2 ones plus exactly 1 ones plus no ones.
Exactly, that's the best way. You have to break it up. There's no way out. Otherwise, you do repetition. I mean, you cannot control the problem otherwise. It's like here, because if you have to control the problem, you don't want to repeat. And there is no way out. Exactly will not repeat, because once you fix those ones, you fix them. There is no ones left over to work with. So there is no way to repeat your process. Okay, any other questions?
So going off of that, actually, let's say the question asked for, does the string have, or how many, what's, if the string had at most 3 ones, you would just write 2 to the 7th times 10 choose 3 plus 2 to the 8th times 10 choose 2, etc., correct?
At most, yeah, it means not none, or exactly 1, or exactly 2, or exactly 3.
Okay.
Period. All right? There's no 3 to the power 7. The minute you introduce your 3 to the power 7, you're going to have repetition. Okay, so as I said, we're going to keep kind of along the same line in a way, and we're going to do some problems which shows up a lot, but we have to really understand this. So this is my simple question here. How many you guys can write it? How many strings can be made from the letters in the word math using every single letter? Very simple problem. So we have math, 1, 2, 3, 4, 1, 2, 3, 4. And how many strings we can make using every letter? So that's 1, of course. And then, they don't have to make any sense. So ATM, right? And so on and so forth. So how many can we make using those quickly? I want the answer quickly.
It would just be 4 factorial.
It's just 4 factorial. Okay, there is no problem. There are 4 different choices for this. There are 3 choices for that spot, 2 for this, 1 for that. So it's nothing more than 4 factorial, or if you want, so just that's a simple permutation. There is no question asked. So that's a 4 times a 3 times a 2 times a 1. Okay. All right. Suppose I ask the same question now, but let me make it clear. But now the same question, but the word Peter. Now, okay, my son's name is Peter, so I use the word Peter a lot. So the same question, but the word is Peter. So here, 1, 2, 3, 4, 5. So I want to use every letter, even if the letter is repeated, I want to use it. 1, 2, 3, 4, 5. Okay. So how many string can I make? I cannot call them word because, they don't have to have any meaning. So we can have this scenario. We can have, I hope I don't come up with something weird, RT, no, I dropped it, RTE, E, P, and so on and so forth. So in how many ways can this be done? Question number 1, is it 5 factorial?
No, because you have 2 non-distinct letters. So P, T, and R are distinct.
Yeah, we have those 2. It means we have a problem.
Could you do 5 choose 2 to pick your E positions and then do multiply by 3 factorial?
That's what we have to do.
Okay.
That's the scenario that we work with it, and then what we're gonna do. So because I have the E, which is repeating, and because of what I did a minute ago, so I first wanna control the E's, pick their position, and you know that they are the same letter. Once I pick their position, I take care of the rest. So that's the way we're going to think about this problem, verbatim, the way I thought about the previous one. So here I have the 5, 2, 3, 4, 5. First, I fix my E's. So there are how many ways to fix the E's? I have to pick 2 positions out of 5. Okay, the position, because it's the same letter. So that to pick the E's, to position the E's. Okay. For every fixed position of the E's, so once I have my E's, I have 3 spots left. But now how many here? I have 3 choices for that. And I have 2 choices for this. And because it occurred only once, so I have 3 choices for that. So for each fixed position of the E's, at some point I start writing this, for each fixed position of the E's, we have 3 factorial, or if you want 3 times 2 times 1, 3 factorial for the rest. So the total number is going to be, we write the total number here. So the total number is going to be 5. We position our e's. Once you position how many other cases we have times 3 factorial. So that's totally based on what we did basically a minute ago. So because one letter repeat, then I have an issue. It's not really permutation anymore, because in permutation, we're assuming letters do not repeat. When we talked about permutation, we talked about distinct object. No, the objects are not distinct, so it's not a regular permutation. Very good. Now the most famous word, and then we try to come up with some kind of a theorem around here. What if I want to, I think I spelled it correctly, Mississippi. The same question, but the word Mississippi. Mississippi have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11. This links, string links 11. Okay, so we have the strings have to links 11, and what we have to put on it is exactly those letters. And the question is again, in how many ways can we do it? And we're gonna think exactly along the same line, no more, no less. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I'll give you 2 minutes, and I want you to think along the same line. I want you to fully understand the picture. Emily, Gina, Rachel, Tim, Simon, go ahead. Nick, Shai. How would you do that?
So I would start with either S or I because they both have 4 and fix those
Okay,
positions.
so we have 4 S's.
So 11 choose 4.
4 S's. So he wants to fix the S's first. Okay, and there are
11 positions, so 11 choose 4.
right.
And then I went down to the I's, so there's 4 I's. So now you have
I's.
7 positions to choose from.
Okay, 4 I's. So now he positions, so he still have 7 to take care of. He positioned the I's. So we have 7 choose 4 also.
And then you have 2 P's to choose from 3 positions.
So 2 P's. Now,
3 choose 2.
right, I have to choose my P's. So I have now 3 positions left.
And then the M is just, you have 1 position to choose from.
And then I have only 1 left, so there is nothing left. I mean, the leftover letter, which is
M.
M, will have to go here. I don't really have, there is 1 place for it to go. Once I fix everybody, so I can put who's 1, for example. Okay, so that's how we're gonna think about, we position the I's. No, sorry, in his case, he positioned the S's. There are that many positions. Once my S is fixed, I start positioning the I's, and I have so many places to put the I's, and I have that many spots for the I's. Now for every fixed position for the S's and I's, so now those are, I still have 3 positions to work with. I have 2 P's, so I choose 2. No, that should be 2.
I said 3 to, yeah, 3 choose 2.
Yeah, yeah. So we have to put 2 positions for the P's out of the 3 positions, and then I'm left with 1 for the M. Okay. So it's like what we did, just exactly the same ideas, exactly the same ideas. Now let us compute that a little bit. So let me compute this. So 3, 2, it means I just started for the last one. So this is gonna give me 11 factorial over 4 factorial, 11 minus 4, that's a 7, times, that's 7 factorial over 4 factorial times a 3 factorial, times 3 factorial over 3 minus 2, which is 1 factorial times 2 factorial. And as you realize, there is a simplification going on, right? This and this go, this and this go, and we're left with 11 factorial over 2 factorial, 4 factorial times 4 factorial. End of the problem. Okay. Any questions? All right, so this pattern, this kind of situation sometimes occur that there is a formula for it. I don't care whether you memorize it or not, but I care about is that you guys understand the picture. But that's really the idea. Suppose you have a collection of an object, not distinct. So I should have forgotten, not necessarily distinct. So they are not different objects, not distinct, not all distinct. Okay, so we have objects, but some of them are repeating. So they are not really all distinct objects. And we have the following scenario. And one of them are of type 1. So it's like here, I have 11 objects. 4 of them are of type S. So, and one of them is of type 1. And those are indistinguishable, like before. And 2, for example, are of type 2, like we had 2 P's. And K are of type K, like we had another 4 I's. And the total number of them is the number of objects. So how many S's plus how many P's plus how many I's plus how many P's is actually equal to 11. Then the number of ordered lists made out of those n object, or to the number of ordered lists made out of this n object, or if you want, the number of a list of length n made out of those is the following, right? I will not show you the formula. We're going a little bit to figure it out. So that's really my problem. So I push this up and I will hide the last piece. Okay, so that's really what my problem is. I have n object, I have n1, the same type, n2 the same type, and 3 the same type. And then I have an object. So it means here, I'm gonna put them as a list. So the list has n length n. So how many I can do? This is exactly what I thought before. I have n1 of the same type. It means I fix n1. In how many ways I can fix them? And choose n1. So I fix n1 of them because they are the same, indistinguishable. Once I place them, I place all those like n2. But how many is left now? The total, I already took away n1. That's exactly what I did in the previous problem. And I keep going. What do I have now? All those of type n3. And how many I have? I already took away n1, and I already took away n2. So we are positional, like the S's, the I's, the P's. But now we're just generalizing. And then I keep going. At the end, I have nk of type K. But then how many I left? Here. What's left is I have to take all the rest away. Means the n1 are gone up to nk minus 1. Okay, I rewrite this because I think it's not very clear. This is n minus n1 plus the last one before it, nk minus 1. Okay, so is this what we did a minute ago? Is this what I did? Yes or no? In my previous problem, I had 11. I had 4 P's.
Yeah, it is.
And this is the i's, this is the p's, and I have one m. So now I'm really generalizing. That's the same logic. But what's nice that this formula becomes simple. And what will become? If I take this and substitute it by it to formula, what's this? This is n factorial over n minus 1 times n1 factorial times. What's this? N minus n1 factorial over n2 factorial times, okay, I should be careful, n minus n1 minus n2. Then I have to multiply it by this term. That's n minus n1 minus n2 factorial divided by, I think you guys see the picture, n3 factorial, and then n minus n1 minus n2 minus n3. And I keep going to the end. At the end, I'm gonna have nk factorial, and here I'm gonna have n minus n1 minus n2, etc., minus nk, and here I will have n minus n1 minus n2 minus nk minus 1. And there is dot, dot, dot. So what's happening at the end? What's gonna be going on? N minus n1 and minus 1, obviously simplifying. That's what happened in the previous problem. This and this will simplify. That's the pattern. This should be factorial. This will simplify with this one. Okay. This is actually going to be 0 because n1 plus n2 plus nk is 0. And this will simplify with the term before it. And what I end up with is n factorial over n1 factorial, n2 factorial, all the way nk factorial. Have you guys seen this before? So this is basically, so if I have an object not distinct, and that's crucial, and we're gonna put them in a list, it's not a permutation anymore because my objects are not distinct. So some of them are repeating. So if I have n1 repeating, n2 and nk repeating, and I have n of them, so the number of ways we can put them in a list, because as I said a million of times, some of them repeat, is given by this formula. And if you simplify it, you get that. The total number divided by how many the first one repeat, factorial, how many the other one repeat, factorial, how many this repeat, and how many that repeat. So let's take one more simple problem along those lines. So any questions?
So this equation is used if they're not distinct.
Absolutely. Means we have nk of them which are the same. And k minus 1 of them is it's the same. Like in the previous one, we had 4 s's which are repeating, 4 i's which are repeating. So they are not distinguishable as objects. So it's not a regular permutation because permutation, we are assuming they are distinct. Those are not, those are changing. So it's not a kind of a permutation. Or sometimes people call it permutation with repeated element. I try to avoid that. All right, so let's take one last scenario along those lines to make the picture a little bit clear. So let us say, very simple scenario. This is my problem. You have 20 of each of the following kind of jelly beans. So you have lots of jelly beans and you're stuck at home bored. And you have some which are red, orange, green, and yellow. And the jelly beans of each color are identical. So all the red are the same, they're not really changing. All the orange are the same, all the green are the same, and so on and so forth. And in how many ways can you put all the jelly beans in a row? So, you know, as I said, you have nothing to do. You have lots of jelly beans and you're gonna put them in a row. You have 20 red, 20 orange, 20 green, 20 yellow, and all the oranges are not numbered or anything. They're exactly the same, and that's crucial. So you can start, you know, putting them. I mean, I'm not gonna put all of them, so you can put them and then you switch. I don't have green, so you can switch and all kind of possibility. You wanna use all of them though. You have all the time in the world. And whatever. So what's the situation here? And you're gonna put them on a line. That's the idea. So what's the situation here? You can put all the jelly beans, all of them, in a row. Just playing till you guys get me the answer. So that's the picture in my mind. I'm just straightening them. All right, anybody who would like to pitch in? Is this similar to the scenario we've been talking about? What do you think?
So would we just end up, so we have 20 of each, so we have 80 total.
We have 80 total.
So
Absolutely.
we would have 80 factorial over, and then 20 factorial times 20 factorial times 20 factorial times 20.
We have 80 total. Absolutely. 20 red, 20 orange, 20 green, 20 yellow. Okay, and you're putting them in order. So what's the thinking? You can think about it in two ways. If you don't like the formula, you can think about it the way we started thinking about this problem. So you have 80 position. Okay, we're gonna do it both ways. 80 position. You have 80 here. So you can first put the red, position the red. That's really the idea. They are all the same. So what I care about only in this problem is their position. So we have 80 spots, we have 20 for the red. That's the red. Once you position the red, you have 60 position left. You put the orange. So position the red for each one of them, the orange. And that's crucial. I told you they are indistinguishable. Otherwise, my logic failed. Now, once you do that, so now you filled in 40 position. And so you still have 40 position. And then now you put in, that's the red, the orange, you put in the yellow. Now you still have 20 position and you have 20 red. There is nothing left to do. Sorry, 20 position and you have 20 red, orange, yellow, 20 green. It means you have nothing else to do. So that's one way to think about the problem. Now, if we do the math here, we're gonna get exactly what this formula tells me. So this is gonna give me 80 factorial for the first, the 60 times 20. And that's where the simplification is coming, because the 60 was the difference between those. So that's why the 60 factorial is being, and then 20 factorial, 40 factorial, times the last one, 40 factorial over 20, the difference is 20. So now we will have 60, 60 simplify, 40, 40 simplify. So the answer is going to be 80 factorial over, and that's what we have the formula. We have 20 of the first type, we have 20 of the second type, 20 of the third type, and finally 20 factorial of the last type. So you can either think about it this way, or you can think about it as how many in total and how many of each type. And you have the freedom of thinking about it the way you want. But I like that because it really explained to me where is this whole thing coming from. Okay. Any questions? All right, Okay, today we're gonna start talking the last minute. I hope you guys started your homework, and if you have any questions, please let me know. So we're gonna start talking a little bit about section 4.6, and we're gonna start talking about the binomial theorem a little bit. And after that, there is another idea about combinatory that I would like to talk about, but I wanna take a break a little bit after I do this section and I go back to it. So things will not be jumble mumble in your head. So Pascal's triangle and the binomial theorem. So most of us have heard of those, but before we mention them, there is this identity that we should know. So tells me that choosing K and choose K is the same as n choosing n minus k. So what do I mean by that? So it means like choosing, suppose you have 10 objects. Choosing 3 objects from 10 is the same thing as choosing 10 minus 3, 7 objects out of 7. Does this make sense? First, let us verify it algebraically. Let's see if algebraically it's correct. Okay, let's compute each one of them separately. The first one is n factorial over k factorial and minus k factorial. The second one is n factorial over n minus k factorial times n minus k. But if you take n minus k, this is going to give you k factorial. So they are algebraically the same. Okay, now you can give me an intuitive reason why those are the same. Why the number of ways you can pick. Remember, now we're choosing 3 subset out of a set of 10 element is the same thing as choosing 7 subset. Is the same number as choosing subset of 7 element out of 10. Does this make any sense? So algebraically is simple. Now can we use the meaning of this also to convince you that they are also the same? Choosing 3 subset, the number of ways we can choose subset of 3 element out of a set of 10 element is the same as the number of ways we can choose 7 subset of 7 element out of 10 element. Does this make sense a little bit intuitively? So suppose I have S that consists of 10 element. Okay, this tells me how many subset of 3. This tells me how many subset of 7. Why do you think those are equal? Can anybody interact a little bit with it? Anybody has any feeling? I mean, algebraically is, as I said, it's the same because that's 10 factorial over 3 factorial times 7. And this is 10 factorial over 7 factorial times 3 factorial. So algebraically, there isn't much to it. But why it makes sense in terms of combinatorics? Why they are the same number? The number of subset with 3 elements of a set of 10 is the same as the number of subset with 7 elements. Anybody?
Because n minus the k equals 3, like 10 minus 7 equals 3, and 10 minus 3 equals 7. So it doesn't matter about the bottle because like the bottle was add together equal to 10 was equal to the n, and
But this is
you
still
showed,
algebraic. Go ahead.
yeah, you show like on the notes that was equal, so they are the same.
Who can give me more combinatoric reason? Okay. So it's a bit hard, but it's not very hard. Why they are the same number? If I pick any subset of 3 elements, any subset. So suppose I'm counting them. I'm counting those. If I pick any subset of 3 elements, the left, to every subset of 3 elements, I can associate the complement in a way, which is 4, 5, 6, up to 10, which have 7 elements. 3 elements, 7 elements. So to every subset of 3 elements, the complement will be a set of 7 elements. So to every one of those, I have one of those. So the number of subset of 3 elements has to equal to the number of subset with 7 elements. Because to everyone with 3 elements, the complement have 7. So the number of those with 3 has to be exactly the number of those with 7, because each one of them correspond one with 7 elements. That's really, algebra is easy here, but that's really what's happening here, because every subset here have 3. Its complement have 7. So if I have 10 of those, their complement will have 10. So I have 10 of those. If I have 100 of those, the complement is going to have 100 of those. So they really have the same number of elements in this set. That's what I meant by a combinatoric proof. It means something that you can really think about what this means to be able to justify the equality between those two. All right, so algebraically, you guys are right, but it's in terms of meaning what's really going on. So if I have 100 of those, I'm going to have 100 of those, because for each one of that, its complement have 7 elements. That's one reason you can think about this equality. Now the binomial theorem, we just stated, and we're going to work with it. So binomial theorem is a theorem, okay, which helped me to do the following. To basically expand x plus y to the 1. So it's a theorem that would help me to expand this expression, okay? So let us state it, and then hopefully next time I give you a very minor idea where it comes from. So the statement. So if I expand it, this is going to be x to the n plus. I'm gonna try to pick the one that the book has, because I can write this in 2 different ways. I'm gonna try to be careful. I don't want to write it not. Okay, plus n, choose 1, x to the n minus 1, y, plus n, choose 2, x to the n minus 2, y squared. So the sum of the power is always n, because when you take a term like this expanded, the sum of the power is always n. Plus, again, n choose 3, x to the n minus 3, y to the power 3. Now, of course, I'm not going to keep working with this forever. So the typical term is, that's the typical term, nk, x to the n minus k, y to the k, plus so on, so forth. The last term is going to be y to the n. Okay, so in sigma notation, this could be written as, we're adding what? We're adding terms of the form n, choose k, x to the n minus k times y to the k, where my k go from 0, that gives me n, all the way to n. So that's what the binomial theorem tells us. So we will do one expansion. But before I do that, let me note one thing. What is N0? Is equal to what? What's N0? Equal to what? Quickly. Think about it in terms of meaning. What does N0 means? The number of ways we can pick subset of 0 element out of a set of n elements. How many subset of 0 element we can pick out of a set of n element? Only one, which is the empty set. So this is equal to 1. So if you think about the meaning of that, it's equal to 1. Or if you want to basically use the formula, this is n factorial over n factorial over 0 factorial, because there's times n factorial. And one reason 0 factorial is 1 is actually, that's the reason why 0 factorial is 1. But assuming that we accept the fact 0 factorial is 1, this is equal to 1. Okay, so when I put n0, this is 1, because if you think about it in terms of combinatorics, it means the number of subset of 0 element in a set of n. There's only one of them, which is the empty set. Okay. So one simple example, and then we have to let go. These are my lecture notes. So let's use this to expand a simple one. Let me use this to expand x plus y, a simple one, because I don't have time for more than that, to the power 3. And let us use this verbatim. So n is 3, so this is x3 plus 3, 1, n is 3, so it's going to give me x squared y plus 3 choose 2, and that's going to be x y squared plus, that's really my last term here. So this should be basically 3, 3, or which is 1, times x0 y to the power 3. So that's really, it's a very good formula to expand. Now we just have to compute. This is x squared y. Now in how many, 3, 1, we can use the formula, or we can ask ourselves in how many ways I can pick subset of 1 element out of a set of 3 elements. This is exactly the 3, or you can compute this. How many ways I can pick subset of 2 elements out of 3? You will get a 3 as well. Now, this is 1, because the number of ways we can pick subset of 3 elements out of a set of 3 elements is only 1. So it's going to give me y cubed. Okay, so that's really how we're going to use it. So next time, I will try to give you an intuitive idea where those combinations coming from, and then we proceed from there. Okay. All right, any questions before we stop? Okay, do you guys have a question about the homework? Okay, so it's due Sunday, and I think you should be comfortable with it. All right? Any questions? Shall we go? Okay, bye-bye for now then. Bye, guys.